Let's dive right into this explainer. Today, we're exploring the evolution of computing, breaking the wall from the abacus to quantum. Throughout history, human ingenuity has essentially formed this unbroken 5,000-year chain of people constantly striving to calculate faster and shatter physical limits. Because computation, right down at its very core, is really just the process of transforming information to get an answer. Whether it's an ancient farmer counting sheep by carving notches on a stick, or some massive, sprawling data center predicting tomorrow's weather, it's all computation. And as we're going to see, every single massive leap forward only happened because the tool that came before it hit a wall.
Just look at this staggering contrast for a second. This is our starting point in the modern era, a room-sized beast of a machine used for World War II artillery, compared to the sleek supercomputer you probably have sitting in your pocket right now. Back in 1946, the ENIAC literally filled an entire room. It weighed 30 tons. It sucked up 150 kilowatts of electricity, which, by the way, is enough to power dozens of modern homes, and all of that just to perform about 5,000 additions per second. Now look at today. Your smartphone effortlessly performs billions of operations a second, fits perfectly in the palm of your hand, and runs all day long on a single tiny battery. It is absolutely a miracle of modern engineering.
But here's a wild thought for you. What if that almighty smartphone still isn't powerful enough? It sounds a little crazy, I know, but it would actually take your phone longer than the entire age of the universe just to simulate exactly how a single caffeine molecule folds. No way, right? But it's true. That massive, staggering gap between what our classical computers can do so effortlessly and what they absolutely fundamentally cannot do at all is exactly the doorway we're about to walk through today.
To really understand why this happens, we kind of have to look back. Human civilization is always running full speed into a mechanical wall. Whenever our need to track sprawling empires, collect taxes, or navigate oceans completely outpaced what the unaided human brain could handle, we built tools. That need drove us from the wooden beads of the ancient abacus, which actually was a pretty brilliant manual positional number system, to the complex gears and dials of the Pascaline. Eventually, that ambition led to Charles Babbage's conceptual analytical engine in 1837, the very machine Ada Lovelace wrote the first algorithm for. But here's the thing, even the best, most perfectly machined gears are slow. And that bottleneck is exactly what pushed us toward early electronic computers like the ENIAC.
So we get electronics, right? But then those early computers slammed right into an electronic wall of insane heat and total unreliability. ENIAC operators were constantly swapping out burnt-out glass vacuum tubes every couple of days. And fun fact, physical moths getting fried inside predecessor machines is literally how we coined the term debugging. To get around this physical wall, we completely ditched those fragile, bulky vacuum tubes, which honestly acted like giant, heavy water faucets, and replaced them with tiny, highly efficient transistors. Made of solid silicone, these little guys acted like microscopic valves. They did the exact same job with a fraction of the size, the heat, and the cost, a total game changer.
In that tiny little microscopic valve, it kicked off the absolute golden era of scaling known as Moore's Law. In 1965, Gordon Moore, one of the co-founders of Intel, noticed that the number of transistors we could economically pack onto a single microchip was roughly doubling every 2 years. Now, this wasn't some strict law of physics, okay? It was really more of a self-fulfilling prophecy, a target the whole industry chased. But it allowed this incredible exponential growth in computing power at a flat cost for over half a century. It's the exact reason we could evolve from massive, clunky mainframes all the way to the specialized CPUs and GPUs that power today's artificial intelligence.
But as always, human ingenuity hit another wall. Today, chip manufacturers have shrunk transistor gates down to just 3 to 5 nanometers. To put that into perspective, that is significantly smaller than most actual viruses. It's so incredibly tiny that a principle we relied on called Dennard scaling just completely broke down around 2005. We simply couldn't control the heat or the power density anymore. Clock speeds totally plateaued, and just like that, we were thrust into the really tricky, deep nanometer era.
And at this unimaginably tiny scale, we slammed into a physical wall where classical transistor behavior just entirely breaks down. The culprit? Quantum tunneling. This is this incredibly strange effect where electrons spontaneously leak right through insulating barriers that, classically speaking, should absolutely stop them dead in their tracks. They literally do not have the classical energy required to cross the barrier, but they just do it anyway. So suddenly, the very foundational physics of the universe becomes this massive, unwanted nuisance for chip makers, causing current leakage and super unreliable switching.
Which brings us to the next massive hurdle, the mathematical wall.
and exactly why classical hardware speeds simply aren't enough anymore.
See, some computational problems really aren't limited by how fast your hardware is or how powerful your cooling systems are. Their mathematical structure is just so exponentially difficult that no amount of classical engineering could ever crack them. We call these NP-hard problems. Take protein folding, for example. The sheer number of possible 3D configurations grows exponentially as the protein gets bigger. Or think about climate simulation, where you literally have to track quantum-level molecular interactions across the entire globe. We absolutely cannot just sit around waiting for classical computers to get fast enough. The math simply outpaces the engineering.
The brilliant workaround to this mathematical wall actually comes from a famous 1981 talk by the legendary physicist Richard Feynman. He hit the nail on the head when he pointed out that nature, at its most fundamental level, isn't classical at all. It's quantum mechanical. So, logically, if the universe operates on quantum mechanics, our computers have to speak that exact same language to simulate it efficiently. Think about it. Trying to simulate complex nature using classical zeros and ones is basically like trying to paint a stunning photorealistic portrait using only 2 colors. So the real paradigm shift here is fundamentally about how we store information. A classical bit is incredibly rigid. It's an independent on-off switch that has to be strictly a 0 or strictly a 1, no in between. But a quantum bit, or qubit, that operates in this wild, blended sphere of probability. Thanks to a crazy phenomenon called superposition, a qubit can exist as a combination of 0 and 1 at the exact same time. On top of that, qubits can become entangled, meaning their states correlate in ways classical bits just can't. This entire setup allows a quantum computer to represent and process an exponentially larger space of possibilities using way fewer physical units.
So what's the big takeaway from all of this? Well, it's that quantum computing is not some alien sci-fi magic that just dropped out of the sky. It is actually the most logical, inevitable next chapter in human calculation. Just like we moved from wooden beads to metal gears and from fragile vacuum tubes to tiny transistors just to overcome physical limits, quantum computing is simply our latest, most profound wall-breaking idea to get past the mathematical and quantum limits of our time. To leave you with a final thought as we wrap up this explainer, quantum computing absolutely transcends classical logic, but it doesn't just throw it in the trash. This whole quantum revolution is standing firmly on a foundation built by 5,000 years of classical computing history. So, my question to you is, are you ready to truly master those foundational binary concepts, the logic gates, and classical information theory, before we take that ultimate quantum leap?